Hi everyone. In this video we're going to start on 1.4 where we connect this whole area problem with the idea of a definite integral. So a lot of what goes on in here is just formalizing what we're doing even a little bit more and attaching some notation to the exact area under the curve as opposed to just the approximate area that we've been working with. So we're going to look back at this picture that should be probably at least somewhat familiar by now. Let's say that we are looking at trying to find the exact area under this curve from A to B. And it looks like I'm using x below, so we'll say this is x and this is y and this is y is f of x. Excuse me if my voice goes cruddy. I have some delightful summer cold that I'm fighting. Okay, so we've already talked about in 1.3 how we would estimate the area under the curve, the area that I've just shaded, using rectangles. So we should be pretty comfortable, I hope, with using a left-hand sum where the height of our rectangle is determined by the leftmost x value, right-hand sum where the height of our rectangle is determined by the rightmost value, x value, and, oh my goodness, this is an M, not a R, midpoint rule, where we use the middle x value in our interval to determine the height of our rectangle. Again, always remember with this one not to be confused with middle y value, and I will even point out that would be a trapezoid rule. I think I snuck in a little problem that makes you at least think about the trapezoid, where if you made a trapezoid who just touched the left and right hand corners and used its area, it would do a little better job. Okay, so anyways, you don't have to do trapezoid here, just pointing it out. I have listed a little bit more of some of the details we came up with last time. To find a specific x value that you're plugging in, you would use that formula right there. So if it's the third rectangle that you're looking for, you would use a plus b minus a over n times 3, or this is also known as your delta x in this one. This part right here is your delta x. Oh, I guess I wrote that here. I'm getting ahead of myself. Okay, so to the big question here, I'm kind of sidetracked on my own summarizing. If we want the exact area instead of the approximate area. So basically what I hope we're spotting is that the more rectangles you use, the better your approximation gets. So the idea would be that if we want exact area instead of approximate area, we would let the number of rectangles go to infinity, or equivalently, we could say that we want delta x to go to 0. So we want infinitely many, infinitely skinny rectangles. I'm kind of delighted right now that that rhymed. Okay, so definition, we're going to actually go for it and say what happens if we do this. So if we can get all of our sums to approach the same value, so left, right, and mid all approach the same value as we take more and more rectangles. And that value should be the exact area under the curve. So if all of those limits approach the same number, and that number is the area under the curve, then we have some vocab and notation that we'll use for that. So we will say f is integrable. I will never say that again actually, but that is the official word for it. That word is always super awkward for me, meaning we can integrate the function. So integrable, we can integrate. Then we will use the notation for integrating, or integrals. Lots of words here. Okay, so the notation for integrating, then we would say that that area, the same one that we have up above, is equal to the integral, big scripty S. Ooh, you know what? I think I even want to sneak something in here. I'm going to write out one of these. The sum, we'll just use left. It doesn't matter which one. I just want to be able to point a couple of things out. I equals, and I'm still not giving myself enough room. Sorry if you're writing and I'm making a mess. 0 to n minus 1 of f of xi times delta x. If we take this and we let n approach infinity, then that should be our exact area. And with integral notation, it would look like this. Okay, so now that I wrote that out, the whole purpose was for me to be able to show you some comparisons. What turns into what in these notations? So it's basically this limit of infinite sum that turns into this big scripty S. So that big scripty S, it's a really tall, skinny S. That is the integral symbol. And that guy means infinite sum. This whole f of xi times delta x is what becomes our f of x dx. More specifically, the delta x, we would think of that as some small but finite change in x, whereas the dx is an infinitely small change in x, infinitely small width of a rectangle. And then with the subscript, the i's, so we had f of xi before, we don't anymore. I would just think of that as by the time we're looking at infinitely many rectangles, we're not saying I hit the first x and the second x and the third x. We're basically saying I hit every single one of those x's, which is crazy to think about because there's infinitely many x's in there. But that's how I would think about that. So convenient things with this new notation, we get the limits of integration. Abbreviating a little there, limits of integration, so the upper limit and the lower limit, those are the ends of our interval. So if we go back up to the top, we were supposed to be finding the area between a and b. That shows up very clearly when you use integral notation. It did not show up quite so clearly when we were using sum notation. Remember, it was hidden in there because the delta x is defined in terms of a and b, but it was not quite so obvious. What we lose is that originally we could see this whole number of rectangles business. We can't see it anymore. That's not a big loss because we know we're now talking about infinitely many. So here's my big thing. When you look at this, I scribbled on it so much that I think I want another color. Green, my favorite green. Okay, we'll say that. I don't know if that's really my favorite. This notation right here is a big deal. So when you see that, that's the integral of function f of x with respect to x from a to b. That is area. When you see that, I want you to be thinking area. There's a little bit of subtlety to this in that area is always positive and integrals are not, but that's what I want your first thought to be. If I'm trying to find the area trapped between a curve and an x-axis, I can represent the exact area with the integral notation as opposed to my Riemann sums that I was doing, my left, right, and midpoint rules that I was doing, where it's just an approximation. Okay, let's see. Last thing, I think I just have a couple of comments. So I said we want the limit of left, right, and mid to all approach the exact area. Really what we want to see is that if you take any Riemann sum, that when you allow the number of rectangles to go to infinity, that approaches one nice value, and that value is the area. So Riemann sums are actually just a broader categorization. With Riemann sums, we're adding up a bunch of rectangles, but it can get a little wacky. We don't have to have all of our subintervals be the same length. So before, where they were all delta x wide, we could have some wide ones and some skinny ones, and that's fine. We also don't have to say that every single height will come from the left side or every single height will come from the right side. We could just say on any given interval, pick an x value, use it to find your height. So Riemann sums allow for a lot more variation in what your rectangles look like and where you're getting the height from. And if you just say in general, it can be any old Riemann sum. You can get as weird as you want with that. You should still get that if you take infinitely many rectangles, they approach the actual area under the curve. Okay, and then last little note on this one, down here at the bottom, we always sum from left to right. If we're going from left to right, then B is always going to be bigger than A. I say always, but then shortly we'll tell you how to do it the other way around. But if we're looking at this problem, we're always thinking that B is greater than A. If that's not true, we're going to have to adjust our thinking, and that's a really big deal. So we're going to assume that B is bigger than A, which means that we conclude that delta X is always positive. If B is bigger than A, then B minus A is positive. Number of rectangles has to be positive, so when we divide, delta X is positive. Okay, so basically what I'm getting at here is that the width of your rectangle is always positive, which means when we get into this little bit of silliness where areas are positive but integrals are not always positive, it's really easy to tell when you're getting those negatives from an integral because it's entirely determined by the y value. If the delta x is always positive, or the dx is always positive, then the sign that you get out of an integral, the positive or negative, is going to come from the f of x part. Okay, so that's the intro to this section. Thanks for watching.